Hello everyone, my name is Zongyao Lyu. I'm a first-year PhD student from the Department of Computer Science and Engineering in the University of Texas at Arlington, and I will be presenting our method for probabilistic object detection via deep ensembles. My team members are Nolan, Aditya, and my supervisor, Dr. William Beksi. In this work, we explore the use of deep ensembles to address the issue of uncertainty estimation in object detection. We applied this technique on several detection models, including cascade RCN, retinal night, grid RCN, and hybrid task cascade as our base detectors. First, I will introduce our data reprocessing method. The test set of the challenge is a subset of the COCO dataset, which consists of 80 distinct classes of objects. For training, we used COCO dataset and filtered out 50 classes in COCO that are not in the challenge. The test and validation sets of the challenge came from video sequences captured from simulation. Since these images were captured in varying lightning conditions, including during the daytime and nighttime, we applied both training and test time augmentations. For training augmentations, we applied were random gamma adjustments, changing brightness and contrast values, and channel shuffle. For test time augmentations, we applied adaptive gamma correction, which heuristically amends images that are either too dark or too bright. Here we can see examples of the test time augmentation with adaptive gamma correction. On the top row, we can see the raw input images, and in the bottom row, we can see their augmented counterparts. For the base detectors in our system, we used 4 existing detection models published in recent few years. Cascade RCN is a multi-stage detection architecture consisting of a sequence of detectors trained with increasing LU thresholds. Retinal night is a fully convolutional one-stage detector using focal laws which applies a modulating term to the cross-entropy laws in order to direct learning on hard negative examples. Grid RCN replaces the traditional box offset regression strategy in object detection by a grid-guided mechanism for high-quality localization. Hybrid task cascade is a new cascade architecture that improves the information flow by incorporating cascade and multitasking at each stage and leverage spatial context to further boost the accuracy. For uncertainty estimation, we used deep ensembles in the challenge. Deep ensembles is a non-Bayesian sampling-based uncertainty estimate technique that trains an ensemble of networks with randomly initialized parameters. Different networks behave differently for given inputs, hence expressing uncertainty. To develop the algorithm that we used to merge the detections from the ensemble, we were inspired by the dropout sampling proposed by Miller et al., in which image detections are grouped into observations. In this procedure, we can see how to actually merge the ensembles. We have to execute this method because detections are not always in order when produced from the neural network. The main hyperparameter in this algorithm is LU threshold, which is a value between 0 and 1. When merging boxes into groups, each box in a group must have an LU with one another of at least LU threshold. In lines 8 through 12, we can see all of the boxes and their associated labels being obtained for a single list of boxes and labels. This list is then passed to NMS match function, which groups these boxes and labels in by LU threshold. And finally, each group is merged into a single box and label by simple averaging. The label depends on the box in a group with the highest confidence score. In this challenge, there are certain metrics we found that can affect the PDQ score. We will dive into some of the implementation details for each heuristic applied to produce our results. First is threshold filtering. To reduce the number of false positives we can remove detections which have confidence scores below a certain empirically obtained threshold. And the second one is bounding box reduction. To reduce the number of background pixels labeled incorrectly, we can reduce the height and width and maintain centers for each bounding box by a certain proportion. The third is improving false positive quality. To increase false positive label quality, we can keep the value of the highest score for each bounding box and set all other scores to 1 minus highest score divided by 30. And the last one is covariance matrix calculation. To increase spatial quality, set the X variance to arbitrary ratio times box width and the Y variance to arbitrary ratio times box height. These values will view the diagonals of the covariance matrix for the top left and bottom right corner of each bounding box. The following are the results from various experiments with both ensembles and single object detectors. The first table here shows the results of hybrid task cascade that we used with different confidence threshold on the validation set. We achieved best results with the confidence threshold of 0.35. The second table shows the results on the other 3 detection models on the validation set. And the third table shows our results on the validation side with ensembles of hybrid task cascade and grid RCN with and without adaptive gamma correction. And we can see that adaptive gamma correction helps improve the performance a little. In the fourth table, we can see our final results on the test site. Our best score was 15959. Well, unexpectedly, we obtained lower scores with our ensemble of hybrid task cascade and grid RCN, and we will review our work to find out the possible reason for that in our future work. And the last table shows the parameter values we used to produce our final results in table 4. 4 parameters we fine-tuned are covariance percent ratio to reduce bounding boxes, threshold for confidence filtering, and IOU threshold for NMS and merging detections. Our proposed method achieved 4th place in the challenge with a PDQ score of 15.959. And there is big space for improvement, and we will keep working on the problem for better performance. Several contributions we made are as follows. First is a new heuristic for improving false positive label quality, and an easy to implement method for merging ensembles of detections, an insight on the effectiveness of test time augmentations with adaptive gamma correction. This is my presentation. Thank you for watching.